And so we will now commence and start the day with our very, very first speaker workshop. And what a way it is to start off Saturday morning here at the Packet Hacking Village in the speaker workshop with a blockbuster workshop. And this morning we have an old friend of ours, and not only an old friend of ours, but also a supporter as well. She is here to present on using machine learning, which is our speaker's passion, and mobile malware. And it is my absolute honor and very big pleasure to present to you the Vice President of Mobile at Veracode, Theodore Titonis.
Thank you so much, Ming. Really appreciate it. And it's a pleasure to be here speaking with you today. You know, I picked 10 a.m. on Saturday morning because I think it weeds out everybody else. So first of all, I commend you for waking up and getting here and being on time. A little bit about my background. You know, as Ming mentioned, my current title is Vice President of Mobile at Veracode. But I came to them via an acquisition. So I was the founder and CEO of a company called Marvin Mobile Security. We launched Marvin at TechCrunch Disrupt in September 2011, and were acquired by Veracode in September 2012. So here we are. And the basis of the technology of Veracode for the mobile application reputation service is largely based on what we did at Marvin with the machine learning. But really quickly, you know, Ming said machine learning is my passion, and we've been working with folks at UC Berkeley since 2008, looking at machine learning to detect malware. And my background is Defense and Intelligence Agency prior to Veracode, prior to Marvin. So what happened there was, you know, some salesperson would go out, have a steak dinner, take another vendor to go golfing, and you know, whatever. They come in, they lay a pile of crap on the table, and they'd say, "Make this work," right? And it was, excuse me, and it was. Let's see, I'll put this in my pocket. Can you hear me okay still? Sorry about that. So, you know, make it work. And there was nothing that we could ever do to make that pile of crap work. So we thought, you know, certainly there's a better way, right? So we started to look at these types of technologies. And what I wanted to do today is really get hands-on to show you, you know, how easy it is to start with Python, with scikit-learn, with some of these technologies to start to classify malware and feeding this data into these algorithms. So quick show of hands just so I can, you know, focus on the right things here today. And who's interested in machine learning? Yes. Yay. Mobile in general? Very good. Awesome. So let's jump right in. The agenda here, I am going to really deep dive into number 5, the machine learning, and spend a lot of time there. But we're going to talk in general about the mobile risk. You know, at Veracode, we focus on protecting the enterprise, where their employees are bringing in these applications on their devices. We'll look at the threats, the vulnerabilities, but I suspect a large majority of you are really familiar with those sort of things. So again, we're going to go through that quickly and dive into the ML. So focusing on the applications, right? Because that's where we see the greatest risk, are the applications for sensitive data loss, you know, from the enterprise, from the consumer. And there's 2 statistics I like to point out on this slide. One being that nearly 50% of the enterprises have already experienced a breach due to a mobile device accessing a network. And the other statistic is on the other side there, where 75% of mobile breaches will come via the apps as opposed to attacks on the devices. And that's projected by Gartner through 2017. But as we think about mobile security, you know, think about the stacks, right? So security's hard, divide and conquer. So in the mobile security stack, the applications are the topmost stack, reliant on all the underlying stacks, right? So at the bottom, we have the infrastructure layer, Verizon, AT&T, right? They're responsible for dealing with their security at that layer, right? making sure there's no DDoS for voice over IP, things like that. Step it up a notch, we have the actual devices. So the infrastructure layer interfacing with the firmware on the devices, Samsung, LTE, Apple, responsible for the device layer security. And then, you take that up a notch to the operating system layer. So Google, Android, Samsung, with all these versions of Android, and iOS, responsible for that layer of security. And then again, at the topmost layer are the applications. And that's really what we're focused on. I'll also stop to say, I think it's my background in computer science, machine learning, big data, that really makes me want to become more scientific, more data-driven with calculating that risk, right? So risk equals probability times impact. And, you start to break down. And I think mobile provides us with that good opportunity to break down and get more scientific in our risk assessment by looking at that probability of these apps making their way onto these devices and the impact of those actual apps. Like, what are they doing? They're not just running on the device. They're connecting to servers located around the world. There's currently an iOS flashlight app that connects to 180 different servers during our behavioral analysis. Like, why is it doing that? So vulnerabilities is Vericode's bread and butter. The top vulnerabilities that we see on iOS and Android for the apps that the enterprise is producing, right? We want to make sure that those apps are secure, free of vulnerabilities, are cryptographic issues. So this is no surprise, right? Crypto is hard on mobile. Think about where are you going to store the key, on the device that could be rooted by another device. Well, it roots the device and can get to the key and all bets are off, right? Okay, so then let's use OAuth, a token-based solution. Let's store the key on the server. Well, what about, when the mobile device can't connect to the server? That app becomes useless. So it's really no surprise that cryptographic issues are the top issues that we see. How many in here build mobile apps? Yeah. Android and iOS. So you guys know, it's not easy. So, and then again, we talk about cryptographic issues just protecting the data in use in transit and at rest. So, at rest, making sure the SQLite database is encrypted, but also, again, in transit, looking at these apps and connecting to these servers that aren't properly pinning their certificates, et cetera. So it's not just an on-device issue when we talk about crypto. So what we like to promote at Vericode is the secure software development lifecycle, right? Not an afterthought, not, getting in your way when you're developing these mobile apps, really making it part of your routine, integrated with the IDEs, every new build, run it through, do a static analysis, look for these vulnerabilities, we'll provide you with remediation options, et cetera. So the top attacks that we see on iOS and Android are MRATs, mobile remote access Trojans, right? So that's similar across the board. Man in the middle, which I think is our next speaker talking about that, big issue. Again, with those certificates not being properly pinned with the data going back and forth, being able to man in the middle. Considerable number of applications, wallet apps, with some gambling apps we can show you where they're storing the key in their code. So man in the middle is an issue. Let's see here. WebKit vulnerabilities, zero-day attacks on iOS. Oh, the certificates and the profiles. I think MobileIron is coming out with some interesting research on this. But, think about it. I could send any of you on an iOS device a link that says, open this, Spearfish, whatever. Open this link on your mobile device. I'll show you a cool app, right? So they open it on their mobile device, and all of a sudden, they've installed a profile that allows me to proxy all their traffic through, my man-in-the-middle proxy to see all their data. So these profiles, these certificates are an issue on iOS, and I see those as a real vulnerability. Profiles in particular with the man-in-the-middle. And then, we all have probably become aware of stage fright and some other recent exploits on Android. I think that the issue with Android, is not that it's insecure because of the open source nature of the code or because it's not the walled garden that Apple provides. But the issue with Android is Google doesn't have a way to update these devices in a timely, efficient way, right? They're reliant upon the carriers. They're reliant on the device manufacturers. So they have no way of getting these updates out there, right? All code has vulnerabilities and insecurities. All software has that. But it's the processes as how we remediate those vulnerabilities that really matters. And I think Android and Google in particular are struggling with that to push these updates out because they're reliant on the carriers. And I think that's why it makes it a more insecure operating system. So, we're jumping into the ML here. Mobile malware detection. Again, why are we doing this? Why are we looking at new solutions? Well, antivirus on mobile just will not work, right? Think of all the signatures. Think of all, how your computer in the wired world just slows down, chug, 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 when the AV is running through all those signatures to see if there's a match on your computer. So we need new ways. On mobile, there's limited CPU, limited memory, battery, so AV isn't going to work. So, even Symantec says AV is dead. And then as we look at these malware samples, again, more of an issue on the Android side. But with iOS, I talked about the inherent issues with the profiles and the certificates, et cetera. But you can see here mobile malware from 2011 to 2014 growing to, about 1.5 million malware samples. And then if we look at, first quarter of 2015, how those are growing as well. So really looking at a threefold growth, I think, from previous Q1 2014 to 2015. So why, mobile malware? Well, a lot of that is financially motivated. And I think as we start to use these devices more for wallets, more for payment transactions, they're tracking devices, right? So there's tons of information, tons of data that can be monetized there, as well as, the real currency stuff with the wallets and, banking credentials, et cetera. All right. So I got through that pretty quickly, and I'm sure all you guys have seen a lot of that before and familiar with it. But this is really, again, where I'd like to spend the majority of our time, is using machine learning to detect mobile malware. So, what we found initially in doing our research, and we used the Windows XP malware data set, right? This was way back in 2008. So, we didn't have 1.5 million variants of Android malware that we're able to train on today. But we used XP because we thought, hey, if we can make it work there, we can make it work anywhere. And let me just step back and say, as I talk about the operating systems for iOS and Android, thank goodness they're Unix-based operating systems that are sandboxed, right? The application, good Lord, if we had to deal with XP on mobile, that would be a disaster. So when we looked at the XP malware, what we found in looking at, what vendors provided signatures for different variants of malware, it really aligned, right, with, vendor one was able to find a lot of Trojans, but missed viruses and worms. Vendor two found a lot of viruses, but missed the worms, missed the Trojans, et cetera. So why does this happen? Well, two things. The vendor becomes really good at, what they're looking for, right? There's a human bias inherent in, what these malware detection, these tools, what they're familiar with. So, human beings aren't very good at getting out of their own biases and really expanding to see different things. So they're looking for what they know, and that's what they find. And their tools are around what they know, and there's some, expertise involved. And, on a whole, if you look at, kind of the whole vendor ecosystem, it's great, great, everybody's finding different things, and that works out. But it really doesn't scale because there's not enough people like you all to go and be able to detect these things at scale. And then, again, we have our human biases. So the correlation between type of malware detected and security vendor, poses a problem with this type of approach. The cognitive bias and the tools that they're using and what they're looking for. And, that there's only a little bit that we can really look for. It really is a needle in a haystack. So, this is going back to 1990, but I think we've really started to see the research trends in using ML to detect malware really grow. Again, 2007, 2008 to today. This only goes to 2011, but you can see the trend and how it's going. So, any Google Scholar search on machine learning to detect malware, you'll see, a lot more research in that realm. And I think, as the machine learning tools become more readily available, now we're talking about deep learning. I don't know if you guys are all familiar with deep learning, where we don't have to train, right? So there's supervised and unsupervised learning, which we'll talk about, where we don't have to train the data, where we can find those correlations and find the malicious binaries without training. It is also going to be very interesting moving forward. So this is our patent on this. It was filed in 2011. So automated behavioral and static analysis using an instrumented sandbox and machine learning classification for mobile security. So what we're doing here is we're doing static and dynamic behavioral analysis on these applications. And it's really important as you're doing this, right? We're talking about calculations, we're talking about statistics. It's really important to have a standard baseline. So on the Android side, we're using emulators because we can really get the data that we need from the Android emulators, and we can scale those in AWS, which is great. But we know our baseline every time. So we know we're measuring CPU, we're measuring memory, threads, we're measuring, the files that are changed on those emulator devices. We're also making it stealthy, right? We're making sure to have the, your number of bars for your carrier go up and down, your battery go up and down, et cetera. Because still these malware variants are going to say, emulator, don't do anything bad, right? Check first thing you write when you write a malicious variant. But so you want to make it stealthy. And it's highly instrumented in detecting all these things. On iOS, we don't have an emulator that will give us that level of data that we need. So we have to actually perform the behavioral analysis on devices. But Amazon just announced actually 2 days ago that AWS is now providing actual devices in their cloud for testing. So we're looking into that so that we can scale there as well. Static analysis, we're looking for things like the vulnerabilities, the cryptographic vulnerabilities. We're looking for API interactions, right? So, does this flashlight app access your microphone? That would be something that would be a predictive feature and probably move it closer to the spyware category than the flashlight category of apps. So I know this is really hard to see, but our patent's been referenced 21 times by folks like Amazon, Trend Micro, FireEye, Qualcomm, Intuit, et cetera. So it's great to see that, this approach is kind of taking off, because I really think this is the future of malware detection on mobile. So again, really bad slide here. Can't see anything. But if you were more interested, this image is out there looking at, how the security domain and the machine learning domain kind of line up. Move past that quickly. And then, this slide is just more talking about that process that we go through using the static and the behavioral analysis, getting all that different types of data, right? So massive amounts of data after we do the static and dynamic analysis. One, small app can produce 1,000 pages of data. So good luck, as a human being looking at that, looking for the needle in the haystack, trying to find, what's malicious in this type of application. The only way to do it is to, put all that data in to these machine learning algorithms. And again, we'll talk about how to visualize this, how these machine learning algorithms work. We've had some difficulty, honestly, in describing this technology in a way that people can understand, right? It's kind of like, oh, you throw all this data into the machine learning black box and, it's like magic. It comes out with a, prediction of maliciousness. And they're like, explain that magic to us a little bit more. So, we've had to get better at that. There's some new visualizations out there that kind of help people wrap their head around what these really advanced algorithms are doing. But the way that you can think about it, and I think it's on my next slide, we'll start to look at, what data goes in and then what you can visualize coming out. So features, we talked about the measuring devices, we talked about the sensors, right? So that's the emulator, that's the static analysis. That's all creating features. And really, you can have a million features basically that go out. But we've, kind of found a sweet spot around 500 or so highly predictive features. So, you're looking at those features. And as a data scientist, I don't know if anybody's played around with scikit-learn, with Python, looking at machine learning. I think you'll find that you spend a lot of time trying to create what's called the design matrix, right? Where you have your features as columns and your binaries as rows. So, you get all that, you find your features, and then you perform your prediction. So in our case, it's binary classification, right? So we're looking and trying to predict malicious applications. And then you select a model, which quite frankly, I think a lot of people get caught up with this as well. And what model should I use? Should I use random forest? Should I use support vector machines? What should I use? You know what? There's something called ensemble machine learning, which basically you throw it into all those, and the algorithm decides what is best. So don't get caught up on the model selection at all. Just use an ensemble and let that decide, whether the random forest provided a better prediction than the support vector machines, etc. So this is kind of how I wanted you to visualize. We talked about, again, the features as columns and the apps as rows. So think of, one column being network traffic, right? So again, a flashlight app that is accessing 180 different servers. Like, why is it doing that? So that would be a feature, right? Another feature would be, trying to root the device. So that's an API, a static code capabilities feature. Network traffic, TCP, UDP, just, again, any number of features. We found for us 500 is a pretty good sweet spot where we can do these predictions in real time. And overfitting is an issue as well. But again, let these models, let the ensemble kind of take care of that for you. So, on the left there is the visualization of kind of how random forest works. You can think of it like a Plinko game where, it's kind of taking those features and it's saying, okay, you go over here, you go over there, but on a very high dimensional space. And I think this is what kind of tricks people up when you start to talk about machine learning in the black box of things is, we as human beings can think about 3 dimensions, maybe 4. This little graphic in the middle, that's 5 dimensions. But try to think about 500. I don't know about you, but my brain explodes. Like, there's no way I can think about 500 dimensions at one time. So that's what these algorithms are capable of doing, is looking at these things, across 500 different dimensions. So, going back to that plot that we saw, with kind of the mountains and at the bottom, there were the dots, on that lower graph. We'll think about that in the way of using machine learning and support vector machines and classification. What will happen is, the spyware apps will all cluster together. The adware apps will all cluster together because of these features, right? And again, across 500 different dimensions, but let's just try to think of it in 3. Spyware over here, adware over here, Trojans over here. And then you have, so you get your flashlight app, a new app that somebody just, uploaded to the App Store. We go out, we perform the static and behavioral analysis. It takes us about 30 minutes or so to get all the data that we need. Send it to the machine learning model that we've trained, and then, come back with a prediction. So 30 minutes or so that takes us. But once we get that, again, in the machine learning black box, you can think of, okay, that flashlight app, whoa, it's way over here next to spyware. It's not, with the rest of the flashlight apps. So that's what, provides that probability of maliciousness, probability of spyware, as opposed to probability of a benign flashlight app. Does that make sense? Oh, good. The nods. Awesome. So, as we talk about this, how do we know that our model is good? How do we know that that spyware cluster is really spyware? And when you're talking about, millions of apps, again, a human can't go in and check all those things. So what we use is what's called area under the curve, AUC. You're familiar, some of the folks that are familiar with machine learning. So what AUC is essentially is the probability that a malicious app ranks higher, right? So probability, we're talking scale of 0 to 1. So malicious app is closer to 1 than our corpus of benign apps. So that's really all that AUC is, the probability that an app is malicious. And what we have to do, because we're talking about malicious and benign, right? There's a cutoff somewhere. What we have to do is find that cutoff in between, where we find that sweet spot of false positive versus false negative, right? And this is where kind of overfitting comes in. We could get really accurate, and some of our models are very accurate, a 0.99 in AUC. So that the curve there, you want to get that curve closest to the 1.0 as you're determining the effectiveness of your model using AUC. So we could get it to 0.99, but we have to find that balance between false positive and false negative. Cross-validation is also very important, right? So you want to use cross-validation to make sure when you take your testing and your training data set, and again, so you're not overfitting. So I'm going to do a demonstration. And before I do that, I don't know, Mac users, hopefully? Good. Okay. So this is how you would set up your Mac environment. So you can brew install, pip install. Really, you want Python and scikit-learn, but this is a good, you kind of have to go in these steps to get it working properly. There's some prepackaged scikit-learn libraries that kind of do all this for you, but it is important to get these steps down. So what we're going to do is kind of go through, and this is this is really just a hello world, if you will, of binary classification, logistic regression. So we're going to generate some data to train with. So this can all happen within sklearn, the data sets. We're going to take a look at how large the data is and what the labels look like. So you'll see a plot that does that. The data is two-dimensional, so not too big, so we can easily visualize it. We're going to see some dots where it's the red as malicious Android apps you can think of, and the green as benign. So look at this code here. You can see PyLab. We're doing the plots here, importing logistic regression from scikit-learn, and generate a classification. Split the data set into training and testing. So think of that logically, right? The training labels, we know that these are no malware. We get a feed every night of 5,000 new Android malware variants and put that into the algorithm. So those are labeled known malware that we can train on. And the unknown is what we get from employee devices and from the app stores as new developers add that. So training and testing is very important. And then we'll visualize the data again, labeling the training points and testing points as white triangles, so you can kind of see where they are in that two-dimensional plot. And then we'll do logistic regression, right? So again, when we do this, when we're actually doing our models, we're not testing on the training data. So that's pretty important to know too. So it's like when we do this step here, it's as if it hadn't seen the app before. So testing on training data is really easy. You'll get a 1.0 AUC every time because you know that it's malicious. But keep in mind that at this step, that's not what we're doing. Set the colors using the predicted class, and then we'll look at our AUC. So that's kind of the last step here. And again, with some print lines, really, this is like 30 lines of code, I think, if you look back at my example. So let's just go ahead and run this. And okay, this is pretty simple. You can see the red are the malicious and the green are the benign. So there's a pretty simple, we'll run through this again and see if they kind of commingle a little bit with the testing set. It's pretty defined. And then you can see the triangles, as I mentioned. This is the training. So that's there that we were looking for. And then there we go. So very easy. Logistic regression finds the line between malicious apps and the benign apps. And then we go back and our AUC is 1.0. So wow, aren't we great? Let's try it again. Let me see if I can get something a little bit more. It's a little bit closer. You can see one more time. That's the problem with using the generated training set. Okay. Let's see where it does the line. Yeah, you can see here, like this one, is it malicious or is it benign, right? So where does that stand? That's where this gets pretty powerful. So then it's able to find that delineator. Let's see what our AUC is again, 1.0. So hopefully that's helpful to you. Not that I expect anybody to like start going out and being able to do this instantly, but really to show you that it's easy to start to get hands-on with this with scikit-learn and Python. And scikit-learn is kind of the first step into this realm. What we use today is kind of well beyond that, but it really is accessible to anyone to start to take your data, and whether it's the static behavioral data from Android or whether it's logs, right? So I think there's huge opportunity using machine learning in network traffic, PCAPs, et cetera, in detecting malware. I think there's a huge opportunity in looking at kind of insiders, exfiltrating data, where you kind of train on that and where you kind of monitor the network traffic going out, the websites visited, et cetera, and then being able to find those outliers. So I think that the machine learning with binary classification in malware detection is just kind of a first step into this really, I think, challenging and important, I think, as we look forward in how we scale to protect these devices. So back to our presentation here, and back to what we're doing with that probability, right? So we take, I talked about it's a probability, 0 to 1.0, but we take that on a 0 to 10 scale. So we've just taken the 1.0 and kind of, to the 0 to 10. And, our hypothesis at the beginning was these malicious apps that we're able to detect in Google Play and the Apple App Store are ending up on employee devices. So, from the beginning, what we found was this trend on the bottom of these top apps, right? So this bar chart shows, 0, there's 23% ones, and then, 2 to 3% nines or tens. So this was the trend that we were starting to see. But what we found with our partnerships with our mobile device management solutions are these apps are actually finding their way on employee devices and really follow that same trend. So we found the average enterprise has 2,400 unsafe applications. So about 3% when you take into account the median and the mean. So 3% of apps that are 8 or above. Some of these are known malware that already have signatures assigned to them. Some of them are detected by the ML with no signatures. So this, is fulfilling to us because our hypothesis is starting to be proven. And because we're in Vegas, we took a look at gambling apps in particular. And gambling apps today, what we found is there's 35 different gambling apps in the average enterprise. So gambling, it's an interesting genre. And being in defense and intelligence, I had to do the security clearance thing. And, my data's now, people have it because of the recent hack. But that's really great. But my point here is with the gambling apps, it's enterprises that are, a little bit more secure. they're concerned that their employees are using these gambling apps. And again, back to, security clearance, it would certainly be flagged as an issue because there would be kind of a propensity for bribery, if you're using, real currency gambling. So that's what's kind of interesting to these enterprises, is kind of taking a look at that, government agencies, et cetera. So we looked at 17 or so of these gambling apps. We found, 4 created by Playtika, 2 by Zynga, 2 by Phantom EFX. So Google doesn't allow real currency gambling apps. Apple does, with the proper licensing and everything in place. In Europe, I think there's already real currency gambling apps in those stores. But this is going to explode. Like this, again, and we look back at cryptography, we look back at those vulnerabilities. This is concerning when people start to really, have real currency associated with these applications. This is a $100 billion industry by 2017. No surprise, right? Look around here. Look at what, gambling, the revenue that it can provide. So, again, these apps are not just running on the devices. They're sending data to and from locations around the world. Looking at these 17 gambling applications, we found, a large number of them use Addicts Tracking as a library. So, all these free apps, this is the way they're monetizing. They're collecting your contact location information, messages, et cetera, and using that to monetize. But Addicts Tracking in particular is sending that to 300 data brokers and advertising networks. So that's an issue. Google, Facebook, of course, collecting massive amounts of data in these applications, and ad exchange. We found with about 9 of these apps, they're recording audio, which is bad, right? They have the capability of recording audio. Hit It Rich Casino Slots accesses your contact information. GSN Casino accesses your social networks. Texas Poker also accesses your social network information. But what we found is, a lot of these apps have hard-coded keys, values, authentication, et cetera. Oh, this is really bad. You can't see this at all. Sorry. But there's just some code snippets here of the bolded area is the hard-coded key. This bottom block of code is showing how it's checking if the device is rooted. So seeing a lot of that. On the other side is kind of our app reputation piece. So again, I think this app is accessing audio information, doing a lot of advertising, et cetera. This is a Slotomania app. Again, on the right, you can see the hard-coded key. This app is sending data, I think, to Ireland and Israel. You can see the data traffic sent there, so bytes sent halfway down on the right. This is 24 megs. Like what? Actually, that's bytes received. I'm sorry. 24 megs. So this app goes out and downloads something that's that big from that server. And then you see policy violating code. The upper left you can't see at all, but it's actually in the clear. So this app was sending most of the data in the clear, except with the exception of the Google data, gender, birthday, and my last login time and date. Oops. Go back. A couple Android examples, just to be safe, like that. Those were iOS gambling apps. These are now Android apps. This is a Wi-Fi Booster app. I don't think it's doing anything but boosting your data, right? I don't know. These people download these apps. Well, how do they think that they're boosting the Wi-Fi? I have no idea. But this app is doing that, and 800,000 people or so have downloaded this app. This is sending data all around the world. It's retrieving your SIM card information, getting your UD, ID information, IMEI, et cetera, monitoring your device location, you're retrieving carrier information and listening for key presses. This is a battery saver app. Again, why 100 million plus people think that this app is going to save their battery, I have no idea. And actually, you see the spiky CPU in the corner. It's draining your battery, right? It's not really saving your battery. Again, sending data to China here. This battery saver app reads your contacts, gets the device identification information, SIM card information, location, carrier, Android account, and also listens for key presses. It's funny, I show these apps, on occasion in presentations, and I find people in the audience like looking at their device and they're like, I have to delete that. I'm glad I'm not seeing it here. Yeah, so we have a directory that's available. We go out every night and get the top 200 apps from each of the top categories. So you would be able to either set up a policy that says, I don't want any apps that are getting my contact information, and then we could alert you to those. So policy it's all about policy, right? So we got to scale to protect this. We can't just do the one-offs. So again, these are very much aligned with what we've learned in the wired world. So protecting sensitive data in use, in transit, and at rest. So we have 180 different policy attributes that you can assign to prohibit these types of applications. So at the top are those different categories, and then the bottom are categories of like what's sensitive to you, right? Is it location information? Is it your messages, your call logs, your browser history? Do you want to prohibit apps that root the device, et cetera? And then, I mentioned our directory. This is, on the right, again, hard to see, but those top apps, and then you could see the policy violations there. So here are the top blacklisted apps that we find in the enterprise from both an iOS and Android perspective. So probably no surprise, Dropbox, Facebook, some Angry Birds, Netflix, et cetera, certainly, for productivity. And that's the challenge here, is finding that balance between enabling productivity that mobile provides, right? That's why everybody's adopting mobile. So enabling productivity, but managing the risk, both the personal risk, which was really our agenda for doing this from the beginning, is like seeing all these apps, seeing, that these devices are essentially tracking devices, and seeing that these apps are just getting massive amounts of user data. It's just it's so concerning to me, and that people don't really care. They're not really treating their data as valuable as it should be treated. And then when we talk about creating these policies, we don't want to take the burden on to create those ourselves, nor do we want you as security experts to take on that burden, alone. That would be a very bad idea to start to create these policies and push those out to your organizations. So we see it as a collaborative effort between the business unit who's wanting these applications for their employees to be more productive. And then also you have to bring in HR and legal to some extent, because there could be something in the terms of particular applications that are concerning. I think we talked about the process. Really, what happens with those policies is they become automated app blacklists. And again, to approach this challenge at scale, you need that. You need an automated way to create these blacklists because, again, as security professionals, we don't want to be the ones that are looking at these millions of apps. And I think by, I think at 2017, there will be 400 billion app downloads. So it's insane to start to wrap your head around how can we protect ourselves against these malicious applications. And I think lastly here, nobody likes to see an infinity symbol when you're talking about work, but it really is kind of a process. And again, we're trying to really make this scientific and using the data from the machine learning, using our background in statistics, computer science, to not be like, oh my God, like this is a huge risk. This is, FUD. Oh no, really being like, here is your calculated risk here. Here is, probability times impact. The impact being, what we see these apps are doing, and the probability being how these apps are ending up on your devices. So it's a continuous process of policy, automated app blacklists, enforcing that on the device, and then assessing that, from a numerical basis, not just a binary, are you at risk or aren't you? So that's what I had for you today. I'm happy to answer any questions. Probably it's a little bit loud in here, so thank you very much for your time.